Okay, we've seen that the ratio of an arc distance to the delta x interval here, an idea familiar from first year calculus, is just the square root of 1 plus f prime of x naught squared. If we consider a normal vector perpendicular to this segment, as in this picture, we conclude that the ratio of the arc distance to the delta x here can be also expressed in terms of the magnitude of n divided by the projection of n in this direction, so that the arc distance can be expressed in terms of delta x by a vector calculation. And we're claiming that by close analogy we can do something very similar to get the surface area above an area increment within, say, an xy plane or an r theta plane. Let's base an intuitive picture on the picture we have here. Let's say that instead of y, this is now the z direction. We have an x direction here, and the y direction is coming up at us from here. So the xy plane would be parallel to the plane of this domino, and z going this way, so that our function values are plotted against the z-axis. I'm not going to relabel this. We just understand now that we're changing our perspective a little bit. If I lay a domino down on the xz plane in the direction of the xz plane, it makes an angle with what would be the xy plane. If this domino is marked so that we have a rectangle whose length is equal to this arc distance and whose width is equal to the width of the domino, then that domino could project down onto another domino, and the dimensions down here would be slightly smaller. In other words, this delta x distance here is less than this distance, and I'm not sure it really comes out looking that way, but done precisely it would. We have a little more length between these points on this domino than we do between these points on this domino, and the ratio of the length of this region to the length of this region being the one that would lie in our xy plane, is equal to the ratio of this arc distance divided by this distance, the ratio of this arc distance to this distance. And that ratio is, in fact, governed by this angle here. That angle is essentially the angle between this domino and this domino, but when we're in 3 dimensions, we can have other orientations. So what we're going to say is we're going to talk about the angle between the normal vector to this domino and the normal vector to this domino. That's going to be the same as this angle, but that angle is going to be the angle between the normal vector to this surface and the z-axis. In this example, the domino has a normal vector in the xz plane. If the domino is also tilted so that its normal vector comes out of the xz plane, then the orientation of this part of the surface with respect to the orientation of this surface is not governed simply by this angle here. The angle becomes more complex, but it's just as easy to handle if we work in terms of normal vectors. And the way that's going to come out is just by the projection of the normal vector on the k direction. That's going to give us the orientation of this surface with respect to the xy plane and give us an angle that we can use to calculate the ratio of the surface area here to the surface area down here in the xy plane.